Advanced language models arrive at the enterprise front door highly proficient in general reasoning, yet completely blind to a company's specific internal logic. Their performance is limited not by their parameters, but by the digital distance between the model and the facts it needs to function. Database architectures reside in BigQuery. Internal runbooks hide in Confluence. Metric formulas are locked in engineers' heads or trapped in legacy metadata catalogs. Clinical? Current architectures fail at the translation layer. When an AI agent attempts to assemble context from these scattered sources, it encounters incompatible APIs and schema mismatches. The silos remain structurally invisible to the agent. To bypass this, engineering teams usually resort to building bespoke, brittle integration pipelines for every individual agent, a manual process that must be rebuilt as soon as the underlying data source changes. Google Cloud published the Open Knowledge Format, or OKF, to establish a common structure for this organizational metadata. It is a 451-line, vendor-neutral specification that formalizes how agents store and consume knowledge using plain Markdown files. By providing a standardized lingua franca for context, OKF moves the industry away from custom integrations and toward a model where internal knowledge is natively portable across any agentic system. This approach draws on the LLM-wiki pattern popularized by researcher Andrej Karpathy. The core premise is that while humans often struggle to maintain complex cross-references, AI agents excel at navigating and updating vast libraries of interconnected text files without fatigue. However, informal wikis lack the strict metadata schemas required for enterprise use. Without a formal structure, organizations cannot reliably port their knowledge bases between different model providers or complex multi-cloud environments. Storing organizational knowledge as versioned code allows these flat files to be managed with the same rigor as software. OKF formalizes this into a standardized directory tree that scales across the entire organization. This bridges the gap between personal documentation and enterprise-grade architecture, turning a flexible wiki pattern into a strict, machine-readable schema. In an OKF bundle, the file path itself defines the concept's identity. For example, a document describing an orders table is stored at tables/orders.md. That path becomes the unique identifier for the agent to reference. Each concept file consists of two distinct parts: a YAML front matter block at the top for structured metadata, and a standard Markdown body below for free-form descriptions and schema details. The format is designed to be minimally opinionated. The type field is the only mandatory requirement in the front matter, categorizing the concept as a table, a metric, or a playbook. Beyond the type, the specification recommends 5 optional fields for richer context: a title, a short summary description, a resource URI linking to the physical asset, classification tags, and a timestamp. To prevent agents from consuming too many tokens during a search, OKF uses a reserved index.md file. This acts as a directory index, allowing the agent to see what knowledge is available before it opens every individual document in the folder. It also includes a log.md file to maintain a chronological history of changes. This ensures the agent and its human curators have a clear record of how the documentation has evolved over time. This minimalistic structure is a deliberate feature. It allows the format to be flexible enough to describe nearly any asset, from a database table in the cloud to a physical incident response protocol. Relationships are created through standard Markdown links. By linking the orders document to a customer's document, the flat file tree transforms into a force-directed relationship graph that agents can navigate to understand data lineage. The specification requires a permissive consumption model. AI agents must be able to parse a bundle, even if they encounter unknown metadata keys or broken links, preventing the system from failing when knowledge is incomplete. This is a major departure from rigid SQL schema registries, which are designed to reject any data that does not perfectly match a predefined model. OKF enforces independence between producers and consumers. A bundle authored by a human engineer can be read by an agent, just as a bundle generated by an automated export pipeline can be browsed in a visualizer. Because the format acts as the contract, organizations can swap their AI models or their data catalogs without needing to re-engineer the underlying context layer. But manual documentation is notoriously difficult to maintain. Who is actually responsible for writing and updating these thousands of Markdown files? To solve the labor problem, Google released a reference implementation called the BigQuery Enrichment Agent to automate the creation of these bundles. In its first pass, the agent performs automated metadata extraction. It walks through a BigQuery dataset and drafts a basic OKF concept document for every table and view it finds. In the second pass, the agent crawls authoritative documentation and query histories, enriching those drafts with join paths, semantic descriptions, and citations. This process shifts the human role from writing documentation to reviewing it. Engineers simply audit the AI-generated metadata for accuracy before it is committed to the repository. OKF is designed to ingest data from existing catalogs, serving as a neutral middle tier that can pull from proprietary systems across the industry. Major platforms like Databricks' Unity Catalog can serve as massive export sources, allowing organizations to convert their existing schemas into conformant, portable Markdown files. By combining automated drafting with human review, OKF provides a systematic way to convert siloed proprietary catalogs into portable, standardized context. It is important to distinguish OKF from other parts of the AI stack. It isn't a replacement for RAG pipelines or a competitor to transport protocols. Think of the stack this way. RAG is the retrieval mechanism, and the Model Context Protocol, or MCP, is the runtime socket. OKF is strictly the static payload that travels through that socket. In a production environment, an MCP server can expose an OKF bundle as a knowledge source. The Markdown file travels through the socket to provide the model with a grounded, verified set of facts. Separating the static context from the active transport protocol makes the architecture more stable. The format remains the same, regardless of which transport mechanism or model is used. OKF doesn't replace existing tools. It formalizes the previously missing layer, where organizational knowledge is described and stored. Moving metadata into flat files brings the discipline of software engineering to knowledge management. Bundles live in Git repositories alongside the code they describe, making documentation traceable and reviewable. Updates to a metric definition or an API schema are handled through standard pull requests. This ensures that every change to what the AI knows is peer-reviewed and version-controlled. This also addresses data sovereignty. Because OKF is file-based, your knowledge assets stay within your own secure infrastructure, bypassing third-party vendor databases. This localized storage supports GDPR compliance by providing a clear, cryptographic audit trail. You can prove exactly which document version an agent referenced at any specific moment. Ultimately, this format provides a strategic defense against vendor lock-in. Your organizational knowledge is no longer trapped in a proprietary catalog's API. By treating context as portable knowledge as code, enterprise architects ensure metadata remains readable, regardless of which cloud or AI model they choose to use in the future.